হ্যাঁ স্যার
একজন
বলুন।
কাউকে কো-হোস্ট করলে ভালো হয় মনে হয়, সে দেখে দেখে আগে সব ঢুকিয়ে।
আমার মনে হচ্ছে আদিত্য থাকবে মনে হচ্ছে।
আদিত্য, ওকে দেখছি না আমি, ওকে আমি দিতে চাইছি নামটা আমি।
হ্যাঁ ও চলে আসবে, একটু পরেই চলে আসবে, মানে গত মিটিং এ তো সেরকমই কথা হয়েছে।
আদিত্য ঘোষকে আমি আমি আপডেট করে দিচ্ছি, জয়েন করছো।
আচ্ছা। আদিত্য চলে আসছে।
হ্যাঁ আদিত্য, হ্যাঁ ভালো হয় মনে হয়, সে দেখে দেখে আগে সব ঢুকিয়ে। আদিত্যকে আমি
আদিত্য থাকবে মনে হচ্ছে।
আদিত্যকে দেখছি না আমি, ওকে আমি চাইছি। হ্যাঁ আগে করে দিয়েছি, আদিত্য করে দিয়েছি কো-হোস্ট।
গত মিটিং এ সেরকমই কথা হয়েছে।
আদিত্য ঘোষকে আমি আমি আপডেট করে দিচ্ছি। না আদিত্যকে বলা হয়ে গেছে, আদিত্যকে পোস্ট করে দিয়েছি, ও করবে এখন।
কি জানি স্যার, কথাগুলো রিপিট হয়ে যাচ্ছে অনেকক্ষণ থেকে।
মর্নিং স্যার।
গুড মর্নিং। আদিত্যকে আমি
আদিত্য থাকবে মনে হচ্ছে।
আদিত্যকে দেখ। আচ্ছা আদিত্য
স্যার গুড মর্নিং।
গুড মর্নিং, বলছি তুমি তুমি কো-হোস্ট আছো, তুমি দেখে দেখে সময় অ্যাডমিট করো।
স্যার এখন এখানে অ্যাডমিট অল হবে, কারণ আমরা সবাইকে পাঠাইনি, আমরা প্রথম 85% পাঠিয়েছি।
না বুঝতে পেরেছি, কিন্তু
হ্যাঁ আমি অ্যাডমিট অল করে দিচ্ছি আর কি।
তুমি অ্যাডমিট অল করলে খেয়াল রাখো যে সমস্ত ম্যানেজ ডিপার্টমেন্টের সব ফ্যাকাল্টি ঢুকতে পারছে কিনা।
হ্যাঁ হ্যাঁ স্যার ঠিক আছে।
সেই জন্য আমাকে দেখে দেখে ডিপার্টমেন্ট করো, তারপরে যাও।
আচ্ছা স্যার ঠিক আছে। স্যার আপনার ওখানে কি ইউটিউবটা লাইভ স্ট্রিম হচ্ছে?
হ্যাঁ হ্যাঁ লাইভ স্ট্রিম হচ্ছে, আমি করে
ওইটা
দিয়েছি।
তাহলে ওইটা একটু মিউট করে দিন, নাহলে ওই আওয়াজটা হয়তো চলে আসবে।
কোনটাকে মিউট করব?
ইউটিউবের যেটা লাইভ স্ট্রিম আপনার মেশিনে যদি হয়, ওটাকে
না
তাহলে একটু।
আমি আমি আমার এখানে রাখিনি ওটা।
আচ্ছা আচ্ছা স্যার ঠিক আছে ঠিক আছে ঠিক আছে।
সেটা হচ্ছে না।
আচ্ছা ঠিক আছে।
হ্যাঁ
ড্রিমলি শুনতে পাচ্ছ?
হ্যাঁ হ্যাঁ আমি পাঠিয়ে দিচ্ছি লিংকটা।
হ্যাঁ হ্যাঁ লিংকটা এখন পাঠাও।
আচ্ছা তোমরা আচ্ছা আমি আদিত্যর সঙ্গে চ্যাটিং করছি, লিখছি আমি তোমাকে।
ওকে স্যার ওকে।
Sir, our speaker has joined.
So, Professor Sharma already just now in the meeting. Sir, good morning, sir. Good morning, Professor Sharma. And just okay, you can unmute. Sir, please, can you unmute once? Just you can unmute.
Unmute. Can you hear me now?
Yes, yes. And it's our pleasure that you have consented to join our this seminar today.
Yeah, it's my pleasure for giving me a chance to be a part of your webinar.
And we are very happy, and it's our honor that you have just today our very special lecture, and you are most welcome to our department.
Thank you, sir. Thanks a lot. I think we are waiting for participants.
Yes,
Some
just
participants
still some participants joining.
Yeah, let us wait for some time. Should I increase the microphone volume a little bit?
You can keep now, just mute for once. When you start, then yes,
Okay.
yes, yes.
Okay. So I'm muting it now.
Yeah, yeah.
Hi. Sir, cannot hear properly. Sir, cannot hear properly.
Hello, now can you hear?
Yes, sir.
Actually, previously no one was talking actually. That's why you are probably not hearing anything.
Okay, sir.
So people are joining, so we'll start within around 5 to 6 minutes.
Okay, sir.
I request all the participants to mute themselves.
Hello.
Good morning.
Good morning, sir.
Yes. Good morning, sir. Good morning.
Hello, sir.
Good morning, sir.
Good morning. Can you hear me, sir?
How much time is required to Good morning, sir. How much time is left to start?
Less than 5 minutes.
वीडियो भी चलेगा आपको वीडियो भी देखना है या
वीडियो भी देखना है
मर जाएगा
Okay, so we are going to start our program now. So I request all the participants to mute themselves. So to our Honorable Dean, School of Basic and Applied Sciences, Professor Bimal Kumar Sarkar, other faculty members from the Department of Mathematics and participants. A very good morning to all of you. Today, we, the Department of Mathematics, are privileged to organize another webinar in our webinar series. We are very glad to inform you that around 240 participants are registered for the talk. But in Zoom, we can accommodate maximum 100 participants. So we have added some alternative YouTube live streaming also. So for smooth running of the video conference, few rules need to be implemented. So dear participant, please follow the rules. Please mute your microphone while the speaker delivers his speech. For any query, please ask him after the speech is over. For YouTube participant, you can raise questions in the comment section of the live streaming, and we will present that in front of the speaker on behalf of you. For any question, raise hand option is also there. So you can do that or you can send a message. Now, I would like to request our Dean, Professor Sarkar, to say a few words about the event.
Namaskar. So it's a very pleasure for myself just to appear in front of all of you learned wisdom persons today in the webinar session just organized by the Department of Mathematics, School of Basic and Applied Sciences. And it's more pleasure for us that today our very, very honored speaker, Dr. Debashish Sharma, Assistant Professor, Department of Mathematics, Gurucharan College, Silchar, Assam, kindly accepted our invitation. And today we have Dr. Sharma with us, and he will be giving just a very important, very interesting talk, the art of counting in the strange world of infinity. Actually, I'm not a person from mathematics, very frankly speaking. So, but I believe that just seeing this title is very interesting, and most probably, I hope, wish also a big success of this 2 days webinar conducted by the Department of Mathematics, School of Basic and Applied Sciences. And it's pleasure for us that today we have with us all learned persons from the department, from the external departments, from different institutions, and also scholars and researchers, students, faculty members are today with us. I know that due to the limitation of this webinar, exceeding 100 participants will not be accommodated in this webinar session online. But there is just a very good just accommodation beyond Zoom. It is just given in YouTube link also. So I expect that it's very happiness for us that many participants also just enjoying this lecture today in YouTube also. So really it's a very big activity just organized by the Department of Mathematics, School of Basic and Applied Sciences. On behalf of the School of Basic and Applied Sciences, myself, Bimal Kumar Sarkar, is welcoming all and wish all the big success of today's webinar. Thank you very much.
Thank you, sir, for your encouraging speech. Now let me introduce our speaker to the participants. Dr. Debashish Sharma is an assistant professor in the Department of Mathematics, Gurucharan College, Silchar. He has a passion for mathematics and is actively involved in various mathematical activities in his region. Since his school days, he had the ambition of pursuing higher studies in mathematics. Dr. Sharma secured first class first in BSc Mathematics honors from Gurucharan College, Silchar in 2009, and thereafter secured the gold medal for MSc Mathematics from Assam University, Silchar in 2011. During his MSc, he received the prestigious NBHM scholarship from 2009 to 11 from NBHM, that is National Board of Higher Mathematics, under Department of Atomic Energy, Government of India. He then completed his PhD from NIT Silchar in 2017. Then he has joined as assistant professor in mathematics in Gurucharan College in 2014. Dr. Sharma works in the combined area of graph theory and linear algebra. In particular, he works in the inverse eigenvalue problems of constructing matrices described by graphs. He has several national and international publications in reputed journals. Dr. Sharma is also the principal investigator of a 3-year project under Teachers Associateship for Research Excellence scheme of Science and Engineering Research Board, that is ACRB under DST, Government of India. The project is jointly implemented by Gurucharan College and IIT Guwahati. He is working on the project in collaboration with Professor Bhavakumar Sharma, Department of Mathematics, IIT Guwahati. Apart from research, Dr. Sharma is actively involved in mathematics Olympiad activities. He has been appointed as an associate member for mathematics Olympiad activities by NBHM. He has delivered several talks and conducted several workshops on mathematics Olympiads. Dr. Sharma likes to interact with students while discussing mathematics as he believes that learning is never-ending process, and the more we interact, the more we learn. Now, without any further delay, I request Dr. Sharma to take over.
Thank you. Thank you. Hello.
Yes, sir. Yes, sir. You are
Yeah.
audible.
Sir, can you hear me?
Yes, sir. We can hear you.
Yeah, okay. So thanks a lot for introducing me and inviting me to join your webinar series. So actually I had visited Adams University also with my sister, who is a faculty there, and it's a very beautiful campus there. And I'm happy to be a part of this talk. So today I'll be speaking on, so I see several participants here. I think 67 here, and in YouTube live also several participants are there. I can begin. So let me share the screen with you. Just if you, the slides, just cross check whether it's visible or not. Yeah. Is it visible?
Yes, sir. It's visible.
No, it should go in the presentation mode. And just wait a minute. I'll just check again. This one. Okay. Yeah. So I think it's visible. The art of counting in the strange world of infinity, right?
Yes, visible.
Okay. So basically, I'll be talking about something that we have been learning since our school days in mathematics. The very fundamental thing that we learn, it's about counting, counting how many objects are there, okay, which we also do in the everyday process. The teachers especially do these things very often while collecting the answer scripts of students. So the counting process is a very important process in the day-to-day life also. So I'll be discussing the process of counting and how to deal with the counting when we go to the world of infinity. That is when we go for infinite sets and all. Okay. So first of all, let me begin with this part, that if you have three objects, say A, B, and C, then in order to count these objects, what we do, we start using the natural numbers, which are also called the counting numbers, right? So we assign the number 1 to A, right? We assign the number 2 to B, right? And yeah, so and we assign the number 3 to C. Okay, so we have three objects here, right? If we have a fourth object now, we assign the number, say, 4 to D. Okay, similarly, if we have a fifth object, so we assign the number 5 to E. Okay, so one thing we should note, that we are not assigning the same number to two different objects, right? Two different objects are not assigned the same number. If we do that, we are actually counting it wrongly. Okay, so I cannot assign the number 1 to A and B both. In that case, I will get only 4 elements, right? Which is not correct. So we should assign a unique number to each object, and two distinct objects should not be assigned the same number. Okay, distinct objects should be assigned distinct numbers. Similarly, the distinct numbers should be assigned to two distinct objects. Okay, so that means, mathematically speaking, we are talking about a bijection. That is a 1, 1, 1, 2 function from the set 1, 2, 3, 4, 5, which I'll denote by I5. It is the set of first 5 natural numbers, okay, to the set S equal to A, B, C, D, E. That is the set of the objects. Okay, so in order to count, we actually construct a bijection from the set of first n natural numbers to the set of objects. Okay, so that n may vary. So if in this example n is 5, there are 5 objects, right? In some other example, it may be, say, 100, 200, anything. Okay, so how we can define the concept of finite sets here? A set is said to be finite if it is either empty or there exists a bijection from in to s for some n belongs to natural number. Okay, So we will say that a set is a finite if we can construct a bijection from the set of first n natural numbers to S for some n. Okay. And if that is not possible for any given n, then S is said to be infinite set. Okay, so that is what we write. A set is said to be infinite if it is not finite. That is, there does not exist any bijection from In to S, okay, for any n belongs to natural number, right? Okay. In the meantime, just let me ask, get it clarified again. Are the slides visible to everyone?
Yes.
Sorry,
Yeah.
I am interfering. Yeah, please make full screen. We are not able to see the full screen view.
Oh, okay, okay. That's what I was having the trouble with.
No, sir, 1 minute.
Yeah.
In everybody's Zoom window, there is a view option is there in the top position. So from there, you can adjust according to your things.
Oh, okay, okay. Yeah, that's why I just, so I'll click on post share first. Your screen is post, more share option. Okay, just let me press stop share now. So in the share screen, I have this. This is the one. No? Is it visible now in full screen?
Yes, sir.
Is it visible in full screen now?
Yes, sir. Yes, sir. It is visible.
Okay, just let me check my. Okay, yeah. Okay, yeah. I have checked in my YouTube also. It's visible in full screen now, right? Yeah, okay. Okay, so I think it's okay now.
Yes, sir. It is clearly visible.
Yeah, okay. So let us proceed. What I was saying is that a set is finite if there is a bijection from the first n natural set of first n natural numbers to S for some n. Okay. So what about I3 and I4 say? Means what happens if In and Im are different? That is n and m are different. Okay. In that case, can there exist a bijection or not? Okay. So let us see this by this example of this I4 and I3. So on the left side, I have kept I4. On the right side, I have kept I3. So that is the domain is I4 and the codomain is I3. And I want to construct a bijection from I4 to I3. Is it possible? Okay. So constructing a bijection or constructing a function is same as putting the numbers on the left side into boxes on the right side, right? So say I put the number 1 in the box 2, the number 2 goes to a different box because I want a bijection. Two different elements should not go to the same place. So suppose I take 2 to the other box, that is 1, and for 3 I take it to the box 3. Okay, but what is the problem with 4? Where will this 4 go? The element 4 has no place to go. If we keep the restriction on of 1-1 map, that is distinct elements go to distinct images. That means if we have more elements on the left side and less elements on the right side, in that case we cannot construct a bijection 1-1 map from In to Im. If n is greater than m, we cannot construct a 1-1 map. Okay. The same way, if n is less than m, we cannot construct an onto map from In to Im. Okay. So this demonstration is actually the illustration of the pigeonhole principle. Okay, which says that if there are say n+1 objects which are to be placed in n boxes, then one of the boxes will have more than one object. Okay? So it's quite obvious, like here there are 4 objects which are to be placed in 3 boxes. So one of the boxes has to have more than one object. Okay. So that means whenever n is not equal to m, we cannot construct any bijection from In to Im. Okay. So this is the basic thing that we know about In and Im so far. Okay. So this is I have written it in a lemma. If n not equal to m, then there cannot exist any bijection between In and Im. Okay. So it's a consequence of the pigeonhole principle, which is a very well-known principle in combinatorics. Okay. And if we consider the contrapositive, the other way, P implies Q, the contrapositive will be not Q implies not P. So the contrapositive is that if there is a bijection between In and Im, then n has to be equal to m. Okay, there is no other option. Okay, so this is the basic principle that we will be using. And so immediately I get another result here. So suppose I am counting a set of objects, I get some number, say there are 10 objects. Suppose somebody else counts the same set of objects and he gets the number as 11. That means there is some problem in the counting process. Okay, so that should not happen, right? So this we can explain using bijections. Okay, let S be a set which is counted in two different ways. Let's say I count S and I get a bijection from IN to IS, IN to S, and I count my friend counts S and he gets a bijection from IM to IS. Okay, then N should be equal to M. So this follows from this principle that composite of bijective mappings and inverse of bijective mapping is also bijective. Okay, so here since it's a map from IN to S, it's a bijection, and G from IM to S is a bijection. So G inverse from S to IM is also a bijection. Okay, so if we consider the composite map G inverse OF, it's a bijection from IN to IM, and by the previous result N should be equal to N. Okay, so what does it say? It says that no matter who counts the elements of a finite set in whatever way. Okay, there are several ways of counting finite sets. In combinatorics, usually these are done, right? In many ways we can count, or many different approaches we can take in order to count how many ways something can be done. Okay, so no matter who counts the elements of a finite set in whatever way, we always end up with a unique IN, right? So that means we can always define something called the number of elements of a finite set. So let S be a non-empty finite set, then the unique number N such that there exists a bijection from IN to IM, IN to S, or equivalently S to IN, because inverse of a bijection is bijection. Then the number N is called the number of elements of S, or it is called the cardinality of S. It is denoted by mod S or card S or hash S. Okay, and for the empty set, the cardinality is defined to be 0. Okay, right. So we have another theorem now, which is also called the addition rule of counting. If A and B are sets such that the number of elements of A is M and the number of elements of B is N, and A intersection B is phi, then the number of elements in the union is just M plus N. Okay, so this also we can prove it by constructing an actual bijection. Okay, so here I just give you the sketch of the proof. Since number of elements of A is M and number of elements of B is N, so there exist bijections IM to F from IM to A and G from IN to B. Okay, so we define a new bijection now, which is H from IM plus N to A union B. It is defined as H of I goes to F of I if I lies between 1 and M, and it goes to G of I minus M if I lies between M plus 1 and M plus N. Okay, so it can be shown that it's a bijection. So you can take it as a task to just show that it's a bijection. These problems are usually given in degree classes. So we have in real analysis course, okay, these problems are done. So if we have disjoint sets, the number of elements in the union is the sum of the number of elements in the individual sets. Okay. Another result that I'll be doing is this: every subset of a finite set is finite, right? So we will proceed through the proof, a sketch of the proof. If S is phi, that is, if S is the empty set, then it's finite by definition. Okay. So let S be non-empty, and we proceed by the induction on the number of elements of T. Okay. So if the number of elements of T is 1, then the only non-empty subset of S is T itself, right? Because a singleton set will have only two subsets. One is phi and another is itself. Okay. So so any non-empty subset of a singleton set is also finite. Okay. So we have the induction hypothesis. Suppose that every subset of a set having k elements is finite. So what we have to prove? We have to prove that every subset of a set having k plus 1 elements is also finite. Okay. Then our proof is over. Okay. So we start with the set T having k plus 1 elements, okay, and let S be a subset of T. Okay, so by definition, since the set T has k plus 1 elements, so there is a bijection from ik plus 1 to T. Okay, and if we consider this particular element f of k plus 1, it is either in S or in or not in S, because S is a subset of T. So the and F is a map from ik plus 1 to T. So every image of every element here is an element of T. Okay? And S is a subset of T. So that image will either belong to S or it doesn't belong to S. Okay? If it belongs to S, then what happens? Since S is a subset of T, if we remove one element, then still this particular thing is a subset. S minus f of k plus 1, it is a subset of t minus f of k plus 1, right? But what is t minus f of k plus 1? It is a set having k elements. T has k plus 1 elements. I have removed one element from T. So it's a set having k elements. And what was our hypothesis? It was that every subset of a set having k elements is finite. Okay. So this T difference, f of k plus 1, every subset of that set is finite. So S difference f of k plus 1 is also finite. So consequently, S is finite, right? And if f of k plus 1 doesn't belong to S, then S is a subset of this set, because f of k plus 1 is not inside S. So even if I remove that particular element from T, still S will be a subset of that set. Okay. So S is finite. So in both the cases, S is a finite set. So that means we have proved that every subset of a finite set is finite. And we have a corollary, which is actually the contrapositive, that every superset of an infinite set will be infinite. Okay. If you take supersets of infinite set, you will always get infinite sets. Okay. Right. So some observations till now that we have made. If A and B are sets such that A is finite and there is a bijection F from A to B, then B is also finite. Okay. That means if we have a known finite set and we construct a bijection from that set to another set, okay, then that another set is also a finite set. That means the comparison need not be between In and the given set always. Okay, if we have a known finite set, we can just construct a bijection from this particular set to another set. Even then, we can conclude whether the other set is finite or not. Okay, so comparison can be done with any finite set. This is what basically it says. And the pigeonhole principle thing, if a number of elements of A is n and number of elements of B is m, and n is greater than m, then there cannot exist any 1-1 map from A to B. Okay. So what is the contrapositive? If there is a 1-1 map, then number of elements in the domain has to be less than or equal to number of elements in the codomain. Okay. And similarly, if number of elements of A is n and number of elements of B is m, and n is less than m, then there cannot exist any onto map from A to B. Okay. So equivalently, if f from A to B is onto, then number of elements of A is greater than or equal to number of elements of B. Okay. So that means we can count and compare the sizes of sets using functions. Okay, right? Okay. So yeah, this is another one. Yeah, if T is a finite set and S is a subset of T, then number of elements of S is always less than or equal to number of elements of T. Okay, so that's quite obvious. We can construct the inclusion map, I from S to T, which is the inclusion map, I of x equal to x for all x. Okay, it's a 1-1 map, and hence number of elements in the domain has to be less than or equal to number of elements in the codomain. Okay, right. So the next result is also a very basic result, that the set of natural numbers is infinite. Okay. So before proceeding with the proof, let me just confirm once again, is the video and everything is okay? Any response?
Yes, it's visible.
Yeah. Okay. Okay. So let me just continue. Right. The set of natural numbers is infinite. So if I have to show it's infinite, what I have to do? I have to show that given any n in natural number, there cannot exist any bijection from n to in. Okay. So to the contrary, let us suppose that there is some bijection. Okay. There is some n that f from n to in is a bijection. So f is 1-1, right? Every bijection is a 1-1 map. Since n belongs to natural number, so n plus 1 is also a natural number. So this is the inductive property of n. Okay, if you have a natural number, you add 1 to it, you get another natural number. Okay, so we have this set I n plus 1. This set is also a subset of the set of natural numbers. Okay, but f from n to in is a bijection. That means the restriction of f from in plus 1 to in is also 1-1. Okay, but this cannot happen. We have seen, if n is greater than m, then there cannot exist any 1-1 map. Okay, so this is the problem that we get. So this cannot happen because n plus 1 is strictly greater than n. That means there cannot exist any n such that there is a bijection between n and in. Okay, so the set of natural numbers is infinite set. Okay, it's not finite. So since every superset of an infinite set is infinite, just now we have seen, so the set of integers is also infinite. The set of rational numbers, that is also infinite. The set of real numbers, that is also infinite, because all these are just supersets of the set of natural numbers. Okay, right. So now we have several questions here. Are there more integers than natural numbers? Are there more rational numbers than integers? And are there more real numbers than rationals? Are there sets having more elements than the set of real numbers? Okay, these are some questions which we will see. Okay, which set has more elements, the integers or the set of natural numbers? Okay, that is what we will see. Which set has more elements, the real numbers or the set of rationals? Okay. And one more thing that we'll see, which is also the theme of this lecture, it's whether the infiniteness of n, z, q, and r is the same. Okay, n, z, q, and r, everything is infinite set. Okay, each of these is an infinite set, but whether the infiniteness of these things is the same or different. Okay, that is what we'll see. If they are different, then how many different types of infiniteness we can talk about? Okay, so these are the questions which we'll try to answer in this particular talk. Okay. So let me go to the next section, that is the countable sets. So from finite sets, we are shifting now to countable sets. We will use the concept of bijections to define what is a countable set. Okay. And since the set of natural numbers is the set that we use for counting, so we'll define everything using the set of natural numbers, right? So a set S is said to be countable if it is finite or if there exists a bijection from N to S. Okay. So the bijection can be equivalently from S to N, because inverse of a bijection is bijection, right? And N is countable as the identity map I from N to N defined by I of N equal to N is a bijection. Okay, the identity map is always a bijection, so N is countable by definition. Then if S is countable and you have a bijection from S to another set T, then we can say that T is also countable. Okay, by this follows by the property of those composite maps. Okay, and a countable set that is not finite, okay, is called a countably infinite set. So the set of natural numbers is actually a countably infinite set. It is countable, but it's infinite. Okay, say the set that I started with, that is A, B, C, D, E. It's also a countable set, but it is finite. Okay, right. So there are two types of countable sets. One is finite set, another is countably infinite set. Okay, and a set that is not countable is said to be uncountable. Okay, any set which is not countable is said to be an uncountable set, right? Okay, so two sets A and B are said to be equivalent. So I introduced the concept of equivalent sets, which is also necessary. Two sets A and B are said to be equivalent if there exists a bijection between them. Okay, so basically they have the same number of elements. Okay, so a set is finite. In terms of equivalent sets, we can say that a set is finite if it is empty or it is equivalent to In for some n. Okay, and in terms of equivalent sets, we can also define countability. A set is countable if it is finite or if it is equivalent to n. Okay, equivalent to the set of natural numbers. Okay, right. So a finite set can never be equivalent to a proper subset of itself. Okay, this is also an interesting result that we'll see. A finite set can never be equivalent to a proper subset of itself. Okay, so the proof basically goes like this. Let S be a finite set having n elements and T be a proper subset of S. Okay, so since it is a proper subset, so we can find at least one element inside S which is not there in T. Okay, so T is a subset of S difference X. If we remove X from S, still T will be a subset of S difference X. Okay, so by lemma 1.5 that we had done, the number of elements of T will be less than or equal to the number of elements of S minus X. Okay, so that is, which is n minus 1. Okay, that is T has at most n minus 1 elements. Okay, so S and T cannot be equivalent, right? So if you have a finite set and if you have a proper subset, there cannot exist any bijection between them. Okay, but the problem begins from here. Is the same true for infinite sets? Okay, whether for infinite sets can you define a bijection between the set and a proper subset of itself? Okay, so this is the question. Are there more natural numbers than even numbers? Which set has more? The set 1, 2, 3, 4, 5, 6, the set of natural numbers, or the set 2, 4, 6, 8, 10, 12. Okay, so I'd like to have some response from the participants. Which set has any response?
I request everyone to mute themselves.
Okay. Okay, so let us go about proceed with this. Which set has from if we just have a look at the sets, it may appear that the set of even numbers has less elements, right? Because the element 1 is not there in n. The element is not there. Okay. So it may appear that the set of even numbers has less. But if we just have a look at this, if we write the even numbers as 2 into 1, 2 into 2, 2 into 3, 2 into 4. Right? In that case, you can see there is a bijection from set of natural numbers to the set of even numbers. Right? So 1 goes to 2 into 1, 2 into 2, 3 goes to 2 into 3, 4 goes to 2 into 4, right? 5 goes to 2 into 5, like that. So,
Dear participants, please mute your audio. We cannot hear.
I think there is an option.
Everyone, please mute your audio and let the speakers.
Yeah, I think there is an option for mute all, or in that case, I will
Dr.
also.
Vijay Kumar Lakshmi, Vijit Ajayak, please mute your audios.
Okay. Okay, so there is a bijection from n to e. Okay. The set of natural numbers to the set of even numbers. Okay. Right. So this is an interesting fact. An infinite set can be equivalent to a proper subset of itself. Okay. For the finite set, it is not true, right? So suppose, so we have just seen what is the example. E is a proper subset of n. E is the set of even numbers. So it's a proper subset of n, which is equivalent to n. Okay, how it is equivalent? We can construct a bijection. The most obvious bijection is this: f of n equal to twice n for all n belongs to natural number. Okay, so we can have a bijection from n to e. Okay, f of n equal to twice n. So this is one bijection. You can construct many other bijections from the set of natural numbers to the set of even numbers. Okay, so this is a bijection. We can prove it very easily. Similarly, the set of odd numbers is also a proper subset of n, which is equivalent to n. Okay, so we can construct the bijection as f of n equal to twice n minus 1 for all n belongs to natural number, right? So this is the case. That means what we have actually proved, we have actually shown that there are as many even numbers as there are natural numbers. Okay, even numbers are not less in numbers, right? There are as many even numbers as there are natural numbers, and there are as many odd numbers as there are natural numbers. Okay, so this is also we have seen, right? And we shall see next that there are many integers as there are there are as many integers as there are natural numbers. We shall also see there are as many rational numbers as there are natural numbers. Okay, so not only the subsets are equivalent to n, even the supersets of n are also equivalent to n. Okay, means even some supersets of n are also equivalent to n. Okay, this is what we will see, right? So that's why I have given the topic as the strange world of infinity. So I'd like to welcome all of you to the strange world of infinity. So integers are not too many. So let us see what is the bijection from n to z. Okay. So from n to z, we can define several bijections can be defined. So I have defined one of them. I take all odd numbers to the positive integers or non-negative integers. I take all even numbers to the negative integers. This is what I am doing. If n is odd, I take n to n minus 1 by 2. If n is even, I take n to minus n by 2. So it's a bijection. You can prove that it's a bijection, right? Okay. So what I have proved, actually, there are as many integers as there are natural numbers. Okay. So I cannot say that there are more integers than natural numbers. So that is the strange thing about the infiniteness. Okay. So at the beginning, it may sound very strange. It sounded strange to even mathematicians when George Cantor first introduced these concepts, right? And yeah, he had to suffer. In fact, he had to suffer a lot of depression because many mathematicians of that time did not believe his theories. Okay, but he is the founder of set theory. So there are as many integers as there are natural numbers. Okay, so visual representation of this particular bijection this way. If we list the integers, so the first element is 0, the second element is -1 because 1 is going to 0, the 2 is going to -1, 3 is going to 1, so 1 is the third element, 2 is the fourth element, right? Then it's -2 is the fifth element, like that. Okay, so that way we can construct the bijection. So this is a way of listing the integers. Okay, right? So many other bijections can also be writing.
This is the last time I'm telling,
Sir,
please
what-
mute your audio, all the participants, please. Please cooperate and mute the audio. Rishika Dubey, Anal Chatterjee, please mute your audio.
Okay. Okay, so let us proceed now. Yeah, we have seen that there are we have already seen two subsets of n which are equivalent to n, right? Now we will do a theorem where we will see that every infinite subset of n is actually equivalent to n. Okay, whatever infinite subset of n you take, it is always going to be countably infinite. Okay, so let us see how we can do it. Okay, so let S subset of n be infinite. So S is not equal to 5. Okay, S is a non-empty set. So it's a non-empty subset of the set of natural numbers. Okay, so we have the natural numbers enjoys a very special property which is called the well-ordering principle. Okay, so by well-ordering principle, so what is that well-ordering principle? Every non-empty set of positive integers has a least element. Okay, we can find out what is the smallest. Okay, every non-empty set of integers, positive integers, has the smallest element. Okay, so S is a non-empty set of integers, so we can find out the smallest element. So let f of 1 be the smallest element. Okay, we denote it by f of 1 because ultimately we are thinking of some bijection, some function. Okay, so then f1 will be greater than or equal to 1 because S is a set of positive integers, so the least positive integer is 1. Okay, so the least element in the set S need not be 1, it will be something greater than or equal to 1. Okay, so since S is infinite, if we remove this particular element f of 1 from S, okay, in that case the resulting set is also infinite. The resulting set is also non-empty, right? At least non-empty, we know, right? So let f2 be the least element of S difference f1. So then f2 is greater than f1 because f1 was the least element of S. Okay, inside S we also had this one, f2 and f1 both were there. So inside S, f1 was the least. Okay, after removing S, f2 is the least. So f2 is greater than f1. So ultimately f2 is greater than or equal to 2. Okay, because f1 is greater than or equal to 1. So f2 is greater than or equal to 2. So by inductive arguments, it can be shown that we can define fn for each n such that fn is the least element of which set of this set, f1, f2, f3 up to fn minus 1. Right, so f3 is the least element of S difference f1, f2. Okay, right, like that. So and f of n is strictly greater than f of n minus 1, so that f of n is greater than or equal to n. Okay, so f from n to S is well defined. Okay, so we have defined a function, right? And we will show that it's actually a bijection. Okay, so since this condition is already there by construction of f of n is strictly greater than f of n minus 1. Okay, so it follows that for n not equal to m, fn is not equal to fm. Okay, then so it's 1 1, right? Distinct elements go to distinct images, so f is 1 1, right? And let S belongs to S be any element. So now we are proving that it's onto also. Okay, that is a surjection. So let us take one element from the set S. Okay, that is the codomain, and we claim that S has to be one of these elements. S has to be either f1, f2, or up to fs. Okay, so to the contrary, let us suppose that S belongs to S difference f1, f2 up to fs. Okay, then f of s plus 1 is less than or equal to S. Okay, so I have written on y. Okay, why is this so? S is an element inside the complement of this set. Okay, F1, F2 up to Fs. Then what is f of s plus 1 should be less than or equal to s. Why this is so? Because by the construction of the function, f of s plus 1 is the least element of this particular set. F of s plus 1 is the least element of this set, and s is an element inside this set. So f of s plus 1 has to be less than or equal to s. Okay. Also, by construction of f of s plus 1 is strictly greater than fs. Okay, and so f of s plus 1 is greater than s also. Fs is already greater than or equal to s. That is also by construction of f. So we have f of s plus 1 is strictly greater than s. Okay, but this particular inequality and this particular inequality, these two inequalities will contradict each other. Okay, so we arrive at a contradiction. Hence, s should be an element inside this set, f1, f2 up to fs. That means f is onto. Okay, why f is onto? Because s will be of the form f of I for some I lying between 1 and s. Okay, so that's why it's onto. So ultimately, we have shown that every infinite subset of n is actually countably infinite. Okay, right. So thus every subset of n is also countable. Yeah. So that also we can say, because every infinite subset is countable, and so the remaining subsets are all finite sets. So they are automatically countable. That means every subset of the set of natural numbers is countable. Again, this is what we have already proved, right? Okay. So this will help us to define some equivalent notations, notions for the countability of sets. Okay, equivalent definitions, right? So every time it is not possible to construct bijections between sets. Okay, because constructing bijection is quite difficult. Okay, so we are lucky that we have this particular result, which says that it is not always necessary to construct bijections to conclude the countability. It is also enough to construct onto maps, one maps under some restrictions. Okay, so let us see what is this. Let S be a non-empty set, then the following are equivalent. Okay, S is countable. There exists an onto map from n to s. Okay, or there exists a 1-1 map from s to n. Okay, so these three are equivalent. So if we can just find a onto map from the set of natural numbers to the set s, then we can say that s is countable. Okay. And or if we can find just a 1-1 map from s to n, in that case also we can say s is countable. Okay, so let us have a look at this proof also. Yeah, so before that I just make a remark. By virtue of composite maps, n in the above conditions can be replaced by any known countable set as necessary in order to establish the countability of s. Okay, so that we can do it. Okay, so let us see the proof. 1 implies 2. So we start from a countable set, right? Let S be countable. So if S is finite, then by definition, we can find an n such that there is a bijection from In to S. Okay. So define G from n to S as G of I equal to Fi for I lying between 1 and n, and G of I is F1 for I greater than n. Okay, then G is onto, right? G is an onto map. So that means what I have done, I have taken the first n natural numbers to their respective positions, and then the remaining natural numbers I have taken it to some element in S, say F1. You may take it to F2, F3, anything, Fn, right? So G is onto, right? So if we have a countable set, it's equivalent to saying that there is a onto map from n to S. Okay. So if S is countably infinite, there exists a bijection. So this case is obvious. If S is already countably infinite, then there is a bijection from n to S. So F is itself the required map. Okay, bijection is also on. So F is the required map. Okay, so the first part we have done. The second part is 2 implies 3. Let F from n to S be onto. So we will be constructing a 1-1 map from S to n. Okay, so how to construct that we see. So since it is an onto map, so if we take any element x from S, okay, then the set F inverse x, which is the set of all pre-images of x, okay, it's a non-empty subset of n, okay, because the function f is from the set of natural numbers to S. Okay, so given any x inside S, we have that the set F inverse x is non-empty subset of natural numbers. So again, we can apply the well-ordering principle. Okay, so by well-ordering principle, it has the least element. So we define G from S to N as G of x equal to Nx, where what is Nx? Nx is the least natural number such that f of nx is x. Okay, and then G is 1, 1. You can show that G is 1, 1, right? So if we have an onto map from n to s, we also have a 1, 1 map from s to n. Okay, so they are equivalent. And then lastly, 3 implies 1. If we have a 1, 1 map from s to n, then s is countable. Okay, so how do you prove that? Since f from s to n is 1, 1, so f from s to fs, that is the range of f. Okay, I take the set of all images. Okay, so then this function is a bijection, but fs is already a subset of n, right? Because f is a function from s to n, so fs is a subset of the set of natural numbers. Okay, and by a consequence of theorem of 2.2, it's countable, right? Every subset of the set of natural numbers is countable. So thus S is countable. So these 3 are equivalent conditions. So we can use any one of them to deal with countability. Okay, right? Okay. Next, I would like to do this theorem. Union of 2 countable sets is countable, right? If you have 2 countable sets and you take their union, you get a countable set. Okay. So let A and B be 2 non-empty countable sets. Then there exist onto maps, alpha from n to A and beta from n to B. We define a function f from n to A union B. Okay. By I take all odd numbers to this alpha of n plus 1 by 2. I take all even numbers to beta of n by 2. Okay, and you can show that it's a onto map. F is an onto map. Okay. So you can do it the other way around also. You take all odd numbers to alpha of n by 2 and take even numbers to beta of n plus 1 by 2. Okay, then it's a onto map. So A union B is countable. So we have used the equivalent criteria. We have not produced a bijection. In fact, this is not a bijection, right? If A and B may not be disjoint. So we have just constructed a onto map from n to A union B. So we can say that A union B is countable, right? Okay. And subset of a countable set is countable. That also can be done. Let A be a countable set and B is a subset of A. So there exists f from A to n, that is 1, 1. Okay, there exists a 1, 1 map from A to n. Then the restriction of f to B is also 1, 1. That means we consider the function taking elements from B only. Okay, so even then it's 1, 1. So B is countable. So every subset of a countable set is countable. Immediately we can look at the contrapositive. Okay, superset of an uncountable set is uncountable, right? If you can construct a uncountable set, and then take any superset of that, it's always also uncountable. Okay, right. So let us see some more countable sets. N cross n, that is the Cartesian product of the natural numbers, set of natural numbers, n cross n, that is also countable. Okay, so we will use that equivalent conditions. We will just construct a 1, 1 map from n cross n to n. Okay, so elements of n cross n will look like order pair n comma n. Okay, so we take nm to the element 2 to the power n into 3 to the power n. Okay, for all nm inside n cross n. Okay, then f is 1, 1. Right, it follows from fundamental theorem of arithmetic. You can easily show, okay, the prime factorization of a number is unique. Okay, right. So from that you can show that this map is actually a 1, 1 map. Okay, but it's not onto map because there are many natural numbers which do not have 2 and 3 as a factor. Okay, there are many such numbers. So it's a 1, 1 map, right? So, but by our equivalent criteria, it's sufficient to claim that n cross n is, to prove that n cross n is countable. Okay, so it follows from fundamental theorem of arithmetic. So there are as many elements in n cross n as in the set of natural numbers. Okay, so this is also a surprising result. Why? Because for finite set, it is not true. If you have a finite set A having say 5 elements, how many elements are there in the cross product? The Cartesian product. The number of elements is 25. Okay, if we have n elements in a finite set, the number of elements in A cross A will be n square. Okay, but for this infinite set, you see the number of elements in n cross n is same as the number of elements in n. Okay, right. So we can have a look at a different approach. This is another way to view countability of n cross n. What is that? We consider this as a graph, right? We plot the points on the horizontal axis. You plot say 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. Okay. On the vertical axis, you plot 1, 2, 3, 1, 3, 1, 4, 1, 5. Okay, that way, just as in graph. And then we can see in the diagram, we start counting from 1 1, then go to 2 1, then you go to 1 2, okay, then go to 1 3, then come back to 2 2, then come back to 3 1, then go to 4 1, okay, then go to 3 2 2 3 1 4 1 5, okay, that way. So step by step we are actually counting all the elements of the set n cross n, okay. And here we have, in fact, we have constructed a bijection here, okay. So you can have a look at the actual expression of this bijection also. You will find it in Real Analysis by Bartel and Sherbert, which is a very good book, okay. So this is a bijection that we have constructed, okay. But the function that I gave you in the earlier slide, that was not a bijection, okay. That was just a 1-1 map, okay. But this is a bijection, right? This one is a bijection, okay. So some more on countable sets. Countable union of countable sets is countable. Okay, we have seen that countable union of two sets is countable, but in fact, if you take a countable collection, so what do you mean by countable collection? Any collection of sets indexed by a countable set. Okay, so here the index, this an, the n is called the index. So the index comes from a countable set. So that collection is called a countable collection, right? So if you have a countable collection of sets, then for each, then their union is also countable. Okay? So we can make use of the fact that n cross n is countable. Just now we have proved. So for each n belongs to natural number. So each of these an is countable. So for each n, there exists an onto map fn from n to an, right? There exists an onto map from fn from n to an. Okay, so we define phi from n cross n to union of this as phi of mn equal to fn of m. Okay, phi of mn is going to the image of m under the map fn. Okay, so in that case, we can show that phi is an onto map. Okay, so it's simple. You take an element from this union, take an element x inside this union, right? So that that element will belong to one of the sets an. Okay, and since fn is onto, so that element we will find out one m inside natural numbers such that fn of m is that element. Okay, so it's quite simple to prove that it's onto. Okay, so this union is countable. Okay, because we have compared it with a known countable set. We already know that n cross n is countable. Okay, so we compare it with n cross n and show that it's countable. Okay, so countable union of countable sets is countable, right? Now we proceed to another question that we had asked in the earlier slides. Can we count the rational numbers? Okay, so in fact, it is true, we can count that the set of rational numbers is countable. Okay, so for that, you see each number in q plus, we break it up into three parts. One is q plus, that is the set of positive rational numbers. So they can be written uniquely as m by n. Okay, so when I say uniquely, I mean that this GCD of mn is 1. Okay, means that the rational number is in its simplest form. Okay, so you can write 1 by 2 as 2 by 4. Okay, you can also write it as 3 by 6. So I am not allowing that. Okay, I am saying that every element here in q plus is written as m by n, where GCD of mn is 1. The greatest common divisor of mn is 1, right? So in that case, the expression is unique. Okay, and so we can define a function f of mn as 5 to the power m into 7 to the power n, just similar to what we have defined earlier. Okay, so in fact, you have to take this two as prime numbers. Okay, you take this two as any prime numbers, you can just prove it. Okay, so then this function is a 1-1 function. It's not 1-2 function. Okay, it's a 1-1 function, but it's a 1-1 function from q plus to n. Okay, so that's why q plus is countable. So similarly, q minus is countable, and by the result that we have done, union of countable union of countable sets is countable. So this union is countable. So the set of rational numbers is actually a countable set. Okay. So what I have proved? I have proved that there are as many rational numbers as there are natural numbers. Okay, this is also a surprising result, right? Given that even between 1 and 2, there are infinitely many rational numbers. Okay, but even then, there are as many rational numbers as there are natural numbers. Okay, this is also quite a surprising result. Okay. So yeah, so listing of countable sets. So any countable set A can be listed in this way. Okay, if you you can list the elements of a countable set as A1, A2, A3, because there is a bijection from N to A. Okay, it's in case of countably infinite, there is a bijection from N to A. So you can list the elements as A1, A2, A3 like that. In some cases, we do that. Okay. Of course, the listing is not unique because the integers can be listed as this 0, -1, 1, 2, -2, or another way 0, 1, -1, 2, -2. Okay, like that. Okay, that way it can be listed. Excuse me. Yeah. So let us see this. So we will use this listing to show that the result of our next section, the set 0, 1 is uncountable. Okay, we will show that it's an uncountable set. Okay, so each number in 0, 1 can be written uniquely as 0.A1, A2, A3, A4 like that. Okay, it means the decimal expansion, right? So where AI belongs to this. So you may say that this expression is not unique. Yeah, it's not unique because say 0.5 can be written as 0.499999 like that. Okay, so that is why we adopt the convention that I am writing this as this, and I mean the expression is unique with the convention that 0 is written as 0.000. Okay, like that, and any other terminating decimal is written in the equivalent non-terminating form by appending an infinite sequence of 9s. Okay. So for example, 0.5 will be written as 0.49999. Okay, and 1 will be written as 0.999. Okay, that is why I have adopted this convention. Okay, so if this set is countable, then what happens? The elements can be listed, right? If 0, 1 is countable, then its elements can be listed as x1, x2, x3 like that. Okay. So what is the x1? X1 will be 0. Some a11, a12, a13 like that. Okay. X2 will be 0.A21, A22, A33, some digits. Okay, X3 will be like that. Okay, so we produce a contradiction here that, or we produce a number here which is not there in this particular list. Okay, then we can conclude that it is not countable. Okay, if it is countable, every element will be there inside this list. Okay, but we will see that we can produce an element which is not there in this list. Okay. In fact, we can produce many elements which are not there inside this list. Okay, so let us see one element which is not there in this list. So this particular argument is called Cantor's diagonalization argument. Okay, so we define y equal to 0.y1, y2, y3, and so on as yi takes the value 2 if aii is not equal to 2, and if it takes the value 3 if aii is equal to 3. Okay. So observe that x1 can be written as is 0.A11, A12, A13 like that. So it is not equal to 0.y1, y2, y3. Why? Because the element yi, that is y1, is not equal to the element aii. Okay, because whenever aii is 2, yi takes the value 3, and if aii is not 2, then yi takes the value 2. That means x1 differs from y in the first place after decimal. Okay, the first place after decimal is different, right? So x1 and x1 and y are different. Similarly, x2 differs in the second place after decimal with y. Okay, so x2 and y are different, right? X3 differs in the third place after decimal with y. Okay, so that's why the element y that we have created is not inside this list. Okay, so in general, y is not equal to xi for all I. Thus, y belongs to 0, 1 is y belongs to 0, 1, but it is missing from the list. Okay, so thus 0, 1 is uncountable. Okay, so 0, 1, the closed interval 0, 1 is an uncountable set. Okay, we cannot count, right? We cannot produce any bijection from n to 0, 0, 1, right? Okay. So some more uncountable sets, immediately it will follow. R is difficult to count. Okay, why? Because 0, 1 is a subset of R, and by the contrapositive of the theorem that we had done, the superset of any uncountable set is always uncountable. So R is uncountable, right? So there are much more real numbers than there are natural numbers. This is what we have shown. There are much more real numbers than there are natural numbers. Okay. Even irrationals are uncountable. Suppose R difference Q is countable, then what happens? Since Q is countable, so their union will be countable. There is R is countable, but this is a contradiction, right? So the set of irrational numbers is also an uncountable set. Okay, so we have seen several uncountable sets, right? And some more interesting results, which I'll tell you. I think I have time. Yeah. Which set has more elements, 0, 1, or the set 0 to 1000, 10,000? Means there are more elements inside the interval 0, 1, or there are more elements inside the interval 0 to 1000. Sorry, 0 to 10,000. Okay. In fact, you will see they have the same number of elements. Okay. There are as many real numbers between 0 and 1 as between 0 and 1000. Okay. That is also a strange result. Okay. And there are as many real numbers between 0 and 1 as there are real numbers between 0 and 10,000. Okay. That means if you have a line of this type, okay, say I'll just use this. If you have a line of length 1, okay, suppose this is a line of length 1, and you have a line of length say 1000, 10,000, right? Then they have the same number of points, right? They have the same number of points. Okay, so that seems quite surprising, right? Okay, so there are as many real numbers between 0 and 1 as there are between 0 and 10,000. So how we can see this? How we can visualize? We can visualize this using a bijection. Okay, so it's very simple to construct this particular bijection, right? F from 0, 1 to 0, 10,000 given by fx equal to 10,000x. Okay, 10,000 multiplied with x. It's a bijection. So for every element in this set, there is a unique element here. For every element here, there is a unique element here. Okay, so it's a bijection, right? So 0, 1, and one more result says 0, 1 is equivalent to any other interval AB. Okay, not only 0, 10,000, 0, 1 closed interval, it is equivalent to any given interval, any closed interval. Okay, so you can take this as the bijection, fx equal to a plus b minus a times of x. Okay, so that is a bijection, right? You can prove it, it's a bijection. There is something more. Any interval AB is equivalent to any interval CD. Okay, any two closed intervals, they are equivalent. Okay, there are as many real numbers between AB as there are real numbers between C and D. Okay, so you can construct this particular bijection, fx equal to C plus D minus C by B minus A into x minus A. Okay, right? Let us see something more. Okay, here, just let me erase this. Okay, 0, 1 is equivalent to closed interval 0, 1 is equivalent to open interval 0, 1. Okay, that is also there. So there are as many real numbers between closed interval 0, 1 and as there are in the closed interval open interval 0, 1. Okay. So if we remove even if we remove 2 points from the closed interval 0, 1, it is having the same number of elements as the closed interval 0, 1, right? So f from 0, 1 to 0, 1 defined as follows. 0 goes to half. Okay, we take 0 to half. Then 1 by n goes to 1 by n plus 2. Okay, and fx and every other element is kept same. So what I am doing, I am taking the element 0. So this 0 is the disturbing element here. So 0 I am taking it to half. Okay, 1 is also the disturbing element. I don't want 1 here. So I am taking 1 to 1/3. Okay, 1 is taken to 1/3. And so what about half? Half has to be taken to something else. So half is taken to 1 by 4, right? 1 by 3 is taken to 1 by, half is taken to 1/4. 1 by 3 is taken to 1 by 5. Okay, like that. 1 by 4 is taken to 1 by 6. That way it goes on. So it's a bijection. Okay, this is a bijection. So there are as many real numbers between in the closed interval 0, 1 as there are real numbers in the closed open interval 0, 1. Okay, so this is also a surprising result. So the closed interval 0, 1 is equivalent to the right half closed interval 0, 1. Also, it is equivalent to the left half closed interval 0, 1. Okay, so the bijection will be something similar to what I have given here, right? And in fact, any such intervals, all are equivalent. Okay, all closed intervals, open intervals, right half open interval, left half open interval, they are all equivalent. Okay, in fact, any such interval is also equivalent to the interval 1 to infinity. Okay, because 0, 1, there are as many real numbers inside 0, 1 as there are real numbers inside 1 to infinity. Okay, So you can visualize this using the bijection fx equal to 1 by x. Okay, take x to 1 by x. Okay, and from the graph also you can see from the graph of 1 by x, every element from 1 to infinity, it will have a unique pre-image in the interval 0 to 1. Okay, so there are as many real numbers between 0 and 1 as there are real numbers greater than 1. Okay, so this is the thing of infinity. In the infinite world, many things become quite strange. Okay, so which set has more elements, 0, 1 or r? Now let us compare which set has more elements, 0, 1 or r. Okay, so in fact you'll see there are as many real numbers in 0, 1 as there are real numbers. Okay, so the set 0, 1, which is a very small proper subset of r, that also has as many elements as there are real numbers. Okay, so we can show it just by constructing a simple bijection. Okay, so all of us we know about the function 10x. Okay, so its domain we can take it as from minus pi by 2 to pi by 2. So in that domain, this function 10x is a bijection. Fx equal to 10x is a bijection. Okay, and also we take 0, 1 to minus pi by 2 to pi by 2. We take it as this g of x equal to pi x minus pi by 2. This is also a bijection. Okay, and the composite of two bijections is a bijection. So f of g, we take f of g from 0, 1 to r, given by f of g of x is 10 of pi x minus pi by 2. That is also a bijection. Okay, so that means we have constructed a bijection from 0, 1 to the set of real numbers. Okay, that is the thing. So the next question is whether all uncountable sets are equivalent. Are there sets bigger than r? Okay, so we have seen r is equivalent to 0, 1. We have seen r is also equivalent to any other interval. Okay, but whether all uncountable sets are equivalent or not, that is the next thing, next big question that we have to answer. And are there sets which are bigger than r, right? And is the infiniteness of the uncountables same? Okay, so at the beginning I said, is the infiniteness of n, z, q and r the same? So we have already seen the infiniteness of n, z, q is same, but the infiniteness of r is much different. Okay, even the infiniteness of 0, 1 is quite different, right? But we will also see that there are many different types of uncountability. Okay, the infiniteness of uncountable sets is also not same. Okay, there are many other sets which are much larger than given uncountable sets. Okay, and we can construct it very simply. The answer lies in a remarkable theorem, but simple theorem by George Cantor, who is the father of set theory, and whatever we are discussing is only due to them, due to George Cantor, the famous George Cantor. Okay, so let us see this particular theorem. If A is any set, then there is no surjection. There is no onto map from A to its power set. Okay, we cannot construct any onto map from A to its power set. Okay, so I'll take some time to explain this particular thing. It's quite confusing. Say, so suppose there is a onto map from A to PA. Okay, then what happens for each element A inside capital A? Phi of A is a subset of A, right? Because the codomain is the power set of A, that is the set of all subsets. Okay, so for each A in the domain, the image phi of A is a subset of A. Okay, so either A is in phi A or A is not in phi A. Okay, so A is an element of A. Okay, and phi A is a subset of A. So it may happen that A is also inside phi A. It may also happen that A is not inside phi A. Okay, so what we do, we define this this set D equal to set of A such that A is not inside phi A. Okay, D is the set of all those elements of A which do not belong to their image. Okay, which do not belong to their image. Okay, then D is a subset of A, so D is an element of power set of A. Okay, but what is phi? Phi is an onto map. So since D is an element in the codomain, we can find a element in the domain such that image of that element is D. Okay, so we can find an A0 inside A such that phi of A0 is D. Okay, so if A0 belongs to, so now there are two possibilities. A0 may belong to D or A0 does not belong to D. Okay, so if A0 belongs to D, then what happens? D is phi of A0, so we can write A0 belongs to phi of A0. Right, but this is again contradicting the definition of D. What is D? D is the set of all those elements which do not belong to their image. Okay, but here I have got an element inside D which belongs to its image. So it's contrary to the definition of D. So that means A naught cannot belong to D, right? And if A naught does not belong to D, then what happens? A naught does not belong to phi of A naught. And so by definition of, if you compare the definition of D, by definition, A naught is an element of D. Okay. So by definition, A naught belongs to D. So again, this is a contradiction. We started with A naught does not belong to D. We ended with A naught belongs to D. So it's a contradiction, right? So none of the cases are possible. That means our initial assumption was incorrect. Okay. This phi is onto. So there is an onto map from A to PA. That is incorrect. So there cannot exist any onto map from A to PA. Okay. So what does this theorem imply? We have seen that a set is countable if there is a onto map from N to S, right? Okay, so if we take S as the power set of the set of natural numbers, then we cannot find any onto map from N to Pn. That means what? Power set of natural numbers is uncountable. Okay, the set of power sets of the set of all subsets of natural numbers is uncountable, right? Not only that, so this theorem actually implies there are many different orders of infinity. Infinity is not the same. Okay, infinite sets are not, the sizes of infinite sets are very much different. Okay, and there is an unending progression of larger and larger sets. Okay, you just keep on taking the power sets, we will get unending progression of larger and larger sets. Okay. So Pn is uncountable because there cannot exist any onto map from N to Pn. So Pn is uncountable set, right? Power set of N. Okay, you take the power set of, again, power set of N is also a set. You take the power set of that particular set. That is also uncountable, but it is again larger than Pn. Okay, the uncountability of Pn is not same as the uncountability of P of Pn. Okay, it is a much larger set. Similarly, PR, the power set of the set of real numbers, is much larger than R. Okay, it can also be shown that, so this is also a very important result, that the power set of natural numbers and the set of real numbers, they are equivalent. Okay, there is a bijection between the set of real numbers and the power set of natural numbers. Okay, so which I am not doing it here, and I am not in a position to do also. I did not prepare this, right? So you can, the interested readers can just have a look at this result, which is available in various texts and even in various sites. Okay, so that's quite interesting. The set of real numbers and the power set of natural numbers, they are equivalent. Okay, so N is said to have cardinality. Yeah, so the next comes the concept of cardinality, or the cardinality for infinite cardinals. Okay, so the least cardinal number is taken as, least infinite cardinal is denoted as LF naught. Okay, so it's just a symbol. It any set which is equivalent to N is said to have cardinality LF naught. Okay, so symbolically, the cardinality of R is denoted as 2 to the power LF naught because of this result, because R is equivalent to Pn. Okay, so number of elements in a power set in case of finite set is 2 to the power N. So that is why this notation is used. Okay, so the cardinality of the set of real numbers or any uncountable set which is equivalent to R is 2 to the power LF naught. Okay, and one more interesting thing that is known as Continuum Hypothesis. It asserts that there is no set whose cardinality lies strictly between LF naught and C. Okay, we cannot find any set, or means the hypothesis says that we cannot find any set whose cardinality lies between LF naught and C. That means we cannot find any set A such that there is a onto map, there is no onto map from N to A, and there is no sorry, I made a mistake. Yeah, we cannot find any set capital A such that there is no onto map from A to N to A, and there is no onto map from A to R. Okay, so in between N and R, we cannot find anything. Okay, that is what the continuum hypothesis says. So this result has not been proved till now. Even it hasn't been disproved. So this is also quite interesting thing. Okay, so we have a infinite sequence of these numbers, LF naught, the cardinality of N. Okay, then the cardinality of Pn, so it will be 2 to the power LF naught. Then the cardinality of P of Pn. Okay, so it's a infinite sequence of your infinite cardinal numbers. Okay, so there are many different types of infinity, many different types of uncountable sets. Okay, there are uncountable sets which are larger than any given uncountable set. Okay, just you take the, if somebody gives you an uncountable set, just take the power set of that set. Okay, you can produce a larger set than the set that your friend gave you. Okay, so there is a infinite sequence of, or infinite progression of larger and larger sets. Okay, so there are many different types of infinities, right? Okay, so with this, I would like to end my presentation here. Thank you. Thanks to the Department of Mathematics, Adamas University, for giving me an opportunity to share my thoughts here. I'd like to hand over the session to the organizers now. Thank you.
Thank you, sir, for your speech. This speech is very enlightening for the beginner, pure mathematicians especially, those who want to study pure mathematics. And of course, this is for us also, because any competitive exam, this type of concepts are very much needed. We know that. So thank you for the session. So now the session will be open for question and answer. So if anyone want to ask any question, one by one, you can ask directly to the speaker. And in the meantime, we are collecting the questions from YouTube and I'll represent that to you.
Okay.
So any question, you can please ask. Okay, so one question is there from YouTube. He or she has mentioned that, please say more about theorem 2.6 with example.
Theorem 2.6
with example.
Okay, let me see. Theorem 2.6. Okay, just let me find it out. 2.6. Is the theorem mentioned? Some means.
No, they want to understand with some more example. So they want some example for the theorem.
Okay, just let me see. Two point. 2.3, 2.5. Oh, okay. Countable union of countable sets is countable. Okay, okay. Okay, so this, how do I explain? Just let me just open one blank sheet here. Okay, so just let me see if I can share this journal screen. Yeah. Okay, I'm sharing this particular thing here. Or yeah, let me try this whiteboard here. Okay. So countable union of countable sets is countable. Okay. So what do you mean by actually countable union? So suppose I have a set, say A1, which is the set, say 1, 2, or say 1. Okay, A1 is the set 1, and I take another set which is indexed by another natural number. Say I take the set 1, 2, and say I take the set A3, which is equal to 1, 2, 3. So in particular, is the screen visible now?
Yes, sir, it's visible.
Yeah.
Yes, sir.
Yeah, okay. Okay. So A3 in general, what I do, I take these sets, the sets of type AI, where the set is I take a sequence of finite sets. Okay, this is what I have done, comma I. Okay, so each of these sets are actually finite. For any given I, this AI is a finite set. Okay, and since the indexing is done, this A1, A2, A3 indexing is done using the natural numbers. That is why this is a countable collection. Okay, any indexing that is done using any countable set, then the collection becomes a countable collection. Okay, so if I take the union of all these sets, A1, A2, A1 union, A2 union, A3, okay, like that. So actually I am taking union of AI such that I belongs to natural number. Then the result says that union will also be a countable set. Okay, so here in this particular example that I have taken, it's a trivial example. So the union of all these sets will be just the set of natural number, which is also a countable set. Okay, so in particular, you can take, say, sets which are indexed by rational numbers. Suppose I take something like this. Okay, suppose I take something indexed by rational numbers. Say for each rational number, I take a set X. For each rational number A, I take a set which is set of all those rational numbers which are X, such that X is rational. And say X is greater than A. Okay, so this here I have indexed it by the rational numbers. So any rational number, given any rational number, we have a set here. So this is also a countable collection because the set of rational numbers is countable. We have already seen. Okay, and if I take the union of these sets, okay, then also we will get a countable set. Okay, so this is basically what the theorem says. But if you take an uncountable union, in that case the union may not be countable. For example, I take this set, I take this collection, say collection of singleton sets. Okay, I take the collection of singleton sets, say AX equal to the singleton X, where X is an element in open interval, say 0, 1. Okay, so this is an uncountable collection because the indexing is happening from the set 0, 1, which is an uncountable set. Okay, so in this particular case, what will be union of AX? Union of AX is the union of all singleton subsets of 0, 1. And what is that? Union of all singleton subsets of 0, 1 is nothing but 0, 1 itself. Okay, which is uncountable. Okay, so uncountable union of countable sets. See, each of these sets are countable, right? Singleton X is a countable set for each X. So even if I take countable sets, but I take uncountably many countable sets, the union may not be countable. Okay, so this is basically what is given by the theorem, right? I hope it's clear that singleton X, the collection of singleton X such that X is in 0, 1, it is an uncountable collection. It is not a countable collection, but it is an uncountable collection of countable sets. Okay, each set in the collection is a finite set, singleton set. Okay, so it's countable, but their union is 0, 1, which is again uncountable. Okay, so I hope it's clear.
Thank you, sir.
Yeah.
Sir, I think when you try to prove something countable and uncountable, maybe countable is easier. To prove something uncountable may be a bit difficult sometimes. So the next question is related to that. Sir, how can we prove a particular set is uncountable?
Yeah, this is what I said. There is no particular rule. Okay, as you can see, there are some tools which are available to us. One of the tools was in order to prove R is uncountable. I have not proved directly that R is uncountable. I have first proved that 0, 1 is uncountable, and then I have used another tool. What was that tool? It was any superset of an uncountable set is uncountable. So that way I proved that R is uncountable. Okay, so this is one of the approaches. There are several other approaches as well. Okay, but this is probably the simplest argument given by Cantor's diagonalization argument. So there are there is no hard and fast procedure or algorithm by which we can show. Okay, say the power set of natural numbers. Okay, it's uncountable. So that also can be shown. Okay, but the process is a little bit different. Okay, so there is no ready-made process available. Okay, the results that I have discussed have already been proved. Okay, and these are taught in classes. Okay, so some basic results. There are some theorems, and we can proceed by the definition that we had given. We will try to find out bijections. Okay. One thing we can always do is we'll try to see whether there is a bijection 1-1 map. Okay, it's easier to construct 1-1 map, so we will try to see whether there is a 1-1 map from that set to the set of natural numbers or not. Okay, that way one of the approaches is this. Okay, other approaches we will try to find out some subsets of that set which are uncountable. Okay, in that way we can show that the given set is uncountable. Okay, so that is what is the approach. Even constructing functions from one given set to another given set is not that easy. Okay, we have seen from 0, 1 to R, we have taken the help of the interval -π/2 to π/2. So it's quite yeah, not quite ready-made, I would say. Of course, it needs a lot of understanding of the theory to prove something, right?
Yes, sir. Thank you. So that means if some set is, we are getting it not countable, means we are not finding any bijective. We can't directly say it is uncountable. We have to use some tools, and then we can finally conclude that.
Yes. Proving
Okay,
uncountable is difficult. We have to show that
Yes, sir.
there cannot exist any bijection. Okay?
Yes, it is.
And proving countable is relatively easy. Why? Because if you are able to find one bijection, then or even one map from that set to n, or onto map from n to that set, then we can come to conclusion. Okay.
Yes, sir. The next question is that this is from the Zoom platform only, from Dr. Lakshmikant Mishra.
Yeah.
Could you please introduce Hilbert's Hotel?
Oh, Hilbert's Hotel, yeah. So that's a quite interesting question, and I know Lakshmi ji. I had been to this Pune University with him in one of the annual foundation schools, so he's my friend. Yeah, so I'd like to thank him for asking me to discuss this Hilbert's Hotel. So it's quite interesting, and I have already discussed it in a different platform. I mean, sir, in a different way I have discussed. So this is what basically I'll just try to explain here. Let me just remove these things. How do I remove? Erase. Yeah. Okay. Okay. So it's famously called the Hilbert's Hotel paradox, or Hilbert's paradox. Okay. So this is basically, suppose you have a hotel which has got several rooms in it. Okay. Yeah, sorry, it's what happened here. Suppose you have a hotel where there are infinitely many rooms, okay, which are numbered from, which are numbered from 1, 2, 3. Okay, these are the room numbers of the hotels. Okay, 1, 2, 3, 4, 5, 6. They are numbered using natural numbers, say. Okay, and yeah, this process continues, and all the rooms are occupied. Suppose there is a situation where all the rooms are occupied. Okay, and some guest arrives. Okay, so can we accommodate that particular guest in the rooms of the hotel? Okay, it is said that all the rooms are occupied. Okay, but even then we can accommodate the guests in the hotel. Okay, that is what we are saying. We are actually so how to go about this process? We will just try to construct some bijections. Okay, I think it's going. Okay, just let me share this part. Okay, the text part is not working properly. Okay, so we have these hotels. So 1, 2, 3, 4, 5, 6. Okay, so these are the room numbers of the hotel. Okay, and we suppose that all the rooms are occupied, but even then I want to accommodate some guests. Okay, so what I do, I use this function f of n goes to n plus 1. That means what I am doing, I am asking the guest in room 1 to shift to the room 2. Okay, so the guest in room 1 goes to room 2. Okay, so f of 1 is 2. So the room 1 becomes vacant. Okay, but there is a guest in room 2 also. So I ask that guest to go to the room 3. Okay, I ask the guest in room 2 to go to the room 3. Okay, so then that way I ask every guest to go to the next room, adjacent room. Okay, and then we will see that the room number 1 becomes empty, and the new guest who has arrived can be accommodated in the room number 1. Okay, now suppose 3 more guests arrive. Okay, and then in that case, what I can do, I can ask the guest n to go to the room n plus 3. Okay, and I will ask every such guest to shift their rooms. Okay, so the guest will be facing some trouble, of course, but it's just an illustration of the fact that we can construct many one-one functions from n to, so starting from a bijection, the case where every room is occupied, it's a bijection, f of n equal to n, that is a bijection. But f of n equal to n plus 1, one room is vacant. In the codomain, the element 1 will not have any pre-image. Okay, so the room 1 is vacant, right? F of n goes to n plus 3. So in that case, 3 rooms are vacant, 1, 2, and 3 are vacant. Okay, so starting from a bijection, we can shift to, but each of these are 1-1 maps. Okay, but they are not onto. Okay, so if a finite number of guests arrive, say k number of guests have arrived, so we can ask each guest to shift to the room n plus k. Okay, so k rooms will be vacated, right? And all the other persons can be occupied in those k rooms. Okay, now if suppose countably infinite number of guests arrive. Okay, so in that case, can we make room for those people? Okay, countable number of guests arrive, countably infinite number of guests arrive, can we make room for those people? The answer is yes. Again, the Hilbert's hotel is a very good hotel. It can make room for those people also. So what functions we can use? We can just ask the guest in room n to shift to the room twice n. Okay, we can ask the guest in room n to shift to the room twice n. So first guest goes to the guest room 2, second guest goes to the room 4. Okay, the third guest goes to the room 6. Okay, so that way all the odd numbered rooms become vacant, right? Because every number is going to an even number, right? Every guest is going to an even numbered room. So ultimately we can vacate all the odd numbered rooms. Okay, and the countable number of guests can be accommodated. Okay, so this is what basically is the Hilbert's paradox. But if if uncountable number of guests arrive, then we cannot find any 1-1 map from that set to n. Okay, so that is the problem. If uncountable number of guests arrive, we cannot, the Hilbert's hotel cannot accommodate those guests. Okay, even if rational number of guests arrive, okay, even then also we can accommodate. Okay, because there is a 1-1 map from rational numbers to n, we can always accommodate that. Okay, so this is basically the concept of Hilbert's hotel, just to illustrate the strangeness of infinite things. Okay, for a finite set, this cannot be done. If there are finite number of hotels, ask first one to go to the second one, third one, fourth one. Ultimately, for the last person, there will be no room left. Okay, so for finite sets, it's not possible. For infinite sets, it's possible. So it basically gives us the idea of the strangeness of the infinite sets. Okay, that is the Hilbert's hotel. I hope it's almost I have been able to explain this.
Yes, sir. Thank you, sir. So the next question is that what is the practical use of this particular domain of mathematics?
Practical use of this particular counting, as in the beginning itself I said, counting is a very fundamental process involved in any practical situation. Okay, but mostly these are actually finding applications in the area of mathematics itself. Okay, with the concept of uncountability, countability. Okay, and in various mathematical results we will use this particular concepts. Okay, and yeah, so it actually it gives us a theory of how we are supposed to count objects. Okay, it gives us a theory for that basis. Okay. Right.
Okay, sir. The next question is from Kukil Rajkhwa.
Yeah.
So So how many visible colors are there? Is it countably infinite or uncountable?
So that may be a question which needs to be asked to an artist. I think it's infinite because there is no limit to artists' imagination. There is no limit to art. Okay, so that is why I have kept the topic as art of counting. So just like there is an infinite number of natural numbers, there are infinite ways of coloring, bringing colors to the lives. So definitely it's there are infinite number of visible colors probably. Maybe in different shades. Okay, maybe the human eyes cannot recognize.
Yes, yes.
Yeah.
The next question is that, can we say that the set of real numbers and complex numbers are equivalent by forming a bijection?
Yeah, in fact, R square, you can take the complex numbers as R square, and we have already seen n cross n to n, there is a 1-1 map. Okay, so R cross R to R, also we can construct an 1-1 map. Okay, and it will be seen that R cross R is equivalent to R. Okay, only power set of real numbers is not equivalent. Power set of real numbers is not, even R cube is equivalent to R. Okay, and in fact, this was the surprising result, which Cantor found and wrote a letter to Richard Dedekind that he is visualizing that there are as many points in the unit square, zero means unit square connecting the vertices 0, 0, 0, 1, 1, 0, 1, 1, as there are numbers, real numbers in the interval 0, 1. Okay, so that was a very surprising, and Cantor also remarked that I see it, but I do not believe it. Okay. So by the virtue of bijection, we have to believe it. Okay, we can construct a bijection from R cross R to R, even R to the power n to R for any given n. Okay, we can construct.
Okay, sir.
Right?
The next question is from Parthapratim Shaha.
Yeah.
Is complement of uncountable set is uncountable?
No, it's not uncountable. Say the complement of R, say R is an uncountable set. What is its complement? It's 5. 5 is a countable set. Complement of uncountable sets need not be uncountable. Okay, there are uncountable sets whose complement is also uncountable. For example, the set of the set 0, 1, open interval 0, 1, that is an uncountable set. Its complement is the union of minus infinity to 1, minus infinity to 0, union 1 to infinity. That is also uncountable. Okay, so need not be. Maybe uncountable, maybe uncountable.
Okay, another question is from Dr. Lakshmikant Mishra.
Yeah.
In view of continuum hypothesis and power sets, can we say that there are countably many uncountable sets up to equivalence?
There are countably many
uncountable sets up to equivalence?
No, how it will be countably many? Because in fact, if you take sets indexed by real numbers, for each real number you define a set, say singleton set. Then that means you take a uncountable collection of uncountable sets. In that case, you can keep on constructing power sets of those sets. So there will be an uncountably many infinite uncountable sets. Okay, so it's not countably many. In fact, it's uncountably many. Okay, we can keep on constructing uncountably many infinite uncountable sets. Okay.
Okay, sir. The next question is from Azimuddin Ansari.
Yeah.
The question is that infinity of the set of real numbers and the set of natural numbers are same or not?
Yeah, it's not same. I have already explained in the video itself. N is a countable set. So in fact, I started from this particular question. Can we say that the infiniteness of N and R is same? So we have already seen it's not same. N is countably infinite, but R is uncountably infinite. Okay, so there are much more real numbers than there are natural numbers. Okay, so this already I discussed. Yeah.
So another small question is that this is regarding Hilbert's Hotel. So Nirjhar Nath has asked that please discuss when odd number of guests come and event is well.
Odd number of guests arrive.
And even is well. So I don't understand that.
That is what I have already explained here. Actually, we can shift all guests to the even numbered rooms. Okay, then all odd numbered rooms will become vacant. If we use the function f of n equal to twice n, ask everybody to go to the room number double of their own room number. So in that case, all odd numbered rooms will be vacant. So we can make the odd numbers room vacant, and we can accommodate all odd numbered guests. Yeah, this also we have seen.
Okay, sir. So hopefully there is no much questions are there. So anyone has any question? Okay, so
Yes, sir. I want to
Sayantan,
ask a question.
yes, yes.
Yeah.
Sayantan.
Yes,
He is
sir.
our student, so he wants to
Yeah.
ask.
Okay.
Suppose in case of Hilbert's hotel, infinite number of people are coming and they
Yeah.
are numbered from 0 to 1.
They are numbered from
0 to 1. Like between 0 to 1, we know there are infinite numbers.
Yeah.
So
And
how can we arrange them?
yeah,
Is it even
in that
possible?
case, we cannot accommodate. We have to close the doors of the hotel because 0, 1 is an uncountable set, and we cannot accommodate uncountable number of guests in a hotel having only countable number of rooms. Okay, in that case, you will need to open another hotel where there are uncountable number of rooms numbered from numbered by the elements in the set 0, 1. Okay, so if there are countable number of rooms, we cannot accommodate uncountable number of guests, right?
Okay, sir. Sir, another question, sir. How we can apply Russell's paradox in our like applications, like in daily life applications? Is it even possible?
Russell's paradox is basically the means it says something about set theory. It's the basis of the set theory. Means we cannot have a set which contains all the sets in the universe. Okay, in that case, there is a means it basically gives us an idea that idea of well-definedness. Okay, whenever we define a set, it has to be means we have to be sure what are the elements inside that set. Okay, so we cannot say that let us consider the set of all sets in the universe. In that case, the contradiction happens, the paradox happens. Okay, so when we define sets, we should be careful that we are sure which elements belong to that set, and that thing is actually called the well-definedness of set. Okay, so in our set theory books, we always see that a set is a well-defined collection of objects. Okay, what does that mean? Given any object in the universe, we should be able to decide whether that object belongs to that set or not. Okay, so in Russell's paradox, what happens if we define something called the set of all sets? Okay, in that case, there will be a confusion regarding whether the set itself belongs to that set or not. Okay, so we have to be careful while defining sets. Okay, we have to be sure which elements belong to the set and which not. Okay. So that is basically the Russell's paradox. Okay.
Okay, sir. Thank you, sir.
Okay, sir. The next question is that could it be possible to use biometric as 1-1 function for our general election procedure to recognize a person?
Yeah, 1-1 functions. Yeah, somebody was asking what are the applications of that countable, uncountable sets. Okay, the best applications that we find is our mobile numbers. Okay, each mobile number has to belong to a unique person. Okay, the identity proof and etc. These things are taken. One mobile number, if one mobile number belongs to two different persons, then there is a confusion, right? So in the election process also, actually we do that. I have also served as an election presiding officer. So what we do is there should be a 1-1-2 correspondence between the voters that arrive in the polling station and the voters that are recorded in the polling register. Okay, there is a list of register which has to be maintained by the polling officer. So if there is no 1-1-2 correspondence, that is, if the number of votes in the voting machine is different from the number of people in the register, then there is a mismatch, and the polling officer is liable to be punished if there is such a mismatch. So actually, this 1-1-2 functions are taken into account when we in our everyday life. Even when we collect the answer script of students, the number of students in the hall should match with the number of answer scripts collected. If it does not match, then there is a problem. Some student might not have submitted, or some answer script is missing. Then the examiners are in trouble. Okay, so obviously the 1-1-2 correspondence has got lots of applications in our day-to-day life, right?
Okay, sir. So I think there are no more questions are there. So anyone want to ask any question? Okay, sir. So there is no more questions. So thank you, sir. for this session. Now I'd like to request our HOD, Dr. Navkumar Mahato, to give the vote of thanks and conclude the session.
Okay, thank you. Good afternoon, everyone. So, good afternoon, sir.
Yeah, good afternoon.
Professor Debashish Sharma. I've listened quietly. Actually, your lecture is very enlightening us, and I have actually moved to my undergraduate and postgraduate level, there where I have seen that is the application of basics of real analysis. That is your mapping, whatever you are told, counting of integers. Nicely you have delivered. Okay, so on behalf of the Department of Mathematics, School of Basic and Applied Sciences, okay, now we got recently this name, School of Basics and Applied Sciences under Adamas University. So we thank you as our speaker. Thank you, sir, for your so important lecture. Not for us only, this for undergraduate and postgraduate students and those who are researchers. And since we are from the mathematical fraternity, so we must know that this is the basic of mathematics. So whenever we are, suppose we are teaching application part, different other subject like differential equation or maybe differential calculus or other. So these are the fundamental things. So one mathematician must know this. Okay, so thank you very much. I also thanks our Chancellor sir, okay, our Vice Chancellor sir, for encouraging us to conduct this kind of webinar series. I also would like to thank you, our Professor Bimal Kumar Sarkar, Dean, School of Basic and Applied Sciences, for his constant support. So without his support, it is not possible to conduct a webinar. I also thanks our participants. There are so many participants I have seen, not only in Zoom medium, there is some more participants are there in the YouTube also. So I thank you all of you, and thank you again, sir, for your nice and informative lecture. Thank you very much.
Thank you very much.
Sir, Professor Bimal Kumar Sarkar, sir, any last comment?
Yeah, really that is very effective, and also we are much grateful to Professor Sharma for his this nice contribution to this event, and we wish that in future also will continue this kind of activity, obviously, and it is in fact a very good platform for sharing our idea, understanding, and almost, and I should say at last that it is one kind of collaborative thinking also. Now, collaborative research and collaborative thinking also, which can obviously contribute something to the bank of knowledge also. Yeah. So it has some very big periphery, not simple this department. So in that way, I'm quite happy that the Department of Mathematics is contributing in this way to the not only mathematics domain, but in the domain of knowledge. Yeah. So that's a very great endeavor from the Department of Mathematics. I'm very happy and thankful to our today very special, our speaker, Professor Sharma.
Thank you very much.
Also much thankful to each and every member of the department, in the school also. Their just a tireless activity only possible to just reach the success. So that today happens. So I'm very happy. Thank you very much. This is my conclusive word. And many thanks to our coordinator who just give this formation today. Should just name Dr. Debashish Sharma also, and also Dr. Aditya Ghosh. Even it is also as a whole, the Dr. Navkumar Mahato, head of the Department of Mathematics. And I should say each and every name of the mathematics department. What just immediately I can just can name Shupriyo, then Shudeep, and then also Shutopa, and then Monimala, each and everybody. So a part and parcel of this activity. So really, it's very good, very nice event. Thank you very much, and hope in future also will continue like this. Thank you very much.
Thank you, sir. So by this word, we can conclude this session. And for the participant, we will be sending one feedback form. Preferably by today night, you can send your feedback. Thank you all.
Thank you.
Shall I close here? End?
Yeah, sir. Yes.
Oh, okay.
Thank you. Thank you very much, everyone. Okay.